talking to you about my work on optimizing human performance using individualized computational models of learning. So I just want to start out by talking a little bit about what I mean by human performance optimization. So simply put, it's about designing interventions to improve human performance. And human performance can be optimized in a number of different domains and in different human applications. So it could be things like cognitive training, it could be things like physical training, and it could even be things like social aspects, like how we construct teams in order to optimize the performance of the members on that team. But for today's talk, we're going to be talking about cognitive training interventions. And in particular, I've been doing a lot of work focusing on understanding intelligent tutoring system-based interventions. So the real challenge for optimizing human performance in the cognitive training space is trying to understand what's the right intervention that you pick in order to improve human performance at the end of the intervention. And so there was a great analysis by Ken Kadinger et al. Showing that even for small design spaces of instructional interventions, so he came up with a small design space that included 15 possible instructional techniques and 3 dosage levels. He showed that even a small space has more than 200 trillion possible designs. So, if you're a instructional designer or a teacher or somebody like even a researcher in education, and you're trying to construct a tutoring system to support people, you have to navigate this space of all of these different options. And it's actually even slightly worse than this. And that unfortunately, we know that the type of instruction that is best can change as the learner progresses. So Kalyuga found that there's this interaction between learners' expertise and which instructional design approaches are actually best for them. These findings are encompassed by an effect known more widely as the expert reversal effect, but the implication of this work is that there's really no one-size-fits-all for instructional design. So there's this added challenge of, not only how do you design a tutoring system that's going to optimize people's performance, but how do you design it when different people may respond differently to different kinds of interventions? So this is a pretty hairy problem, and my work is really looking at how we might deal with this problem. So currently, the most widely used approach to addressing this is to conduct A/B experiments, or to compare possible interventions. So that for cognitive training interventions, this might include going into a classroom, getting access to students, identifying when that particular intervention fits in with the class curriculum, and then running some kind of a study, a randomized study comparing 2 different interventions to see which one produces the best performance. As a result of all of these considerations, running A/B experiments is pretty expensive and time-consuming, and at the end of the day, it really only gives you information about just a few interventions. So in this case, it's only giving you information about 2 interventions. If you want to design a new intervention, then you're going to have to run another A/B experiment to test it. And if you come up with another one after that, you have to run another A/B experiment. So it's this very slow process of testing each particular intervention. So is there any way that we can reduce the cost and the time needed to test these different interventions? So to overcome this problem, I look to the way that engineers solve problems like bridge design. In particular, I'm looking at how they use simulation to reason about different interventions before deploying them in the world. So in this case, an engineer might test a bridge design to make sure that it's going to be structurally stable before they actually build it and try driving a truck over it. Analogously, I argue that we can use agent-based simulations to explore possible interventions before we deploy them in the classroom. So flipping back to this example, your typical A/B experiment where you're randomizing people between different conditions, I'm proposing that instead of having human students in this A/B experiment, we run an A/B experiment with simulated agents in order to predict performance for these alternative interventions. So the interesting thing about this approach is that it's pretty cheap, so that we can run a lot of different simulations. And it's easy to test different alternatives beyond those that we might have had when we ran the initial study. So maybe we come up with a 3rd intervention, intervention C. We don't have any data. That's just an intervention that I just came up with, but we can construct a simulation and test it and see how it might compare to the other interventions that we've come up with. So this makes it possible to reason about, interventions that are known and that we might have some human data for, but it also enables us to reason counterfactually about interventions that we don't have any human data about those conditions. So to explore this idea, we used a fraction arithmetic tutor designed by Ronnie Patel. And I just have a few screenshots of the fraction tutor in the upper right there. Now, Ronnie built this tutor to investigate the question of whether it's better to block or interleave fraction arithmetic instruction. And in this tutor, students received 3 different kinds of problems. They received fraction addition with same denominators, fraction addition with different denominators, and fraction multiplication problems. And Ronnie ran a study with this tutor where students were randomized to either receive all the problems of the same type in successive blocks, so all the fraction addition same, then all the fraction addition different, then all the fraction multiplication, or they were put into an interleaved condition where they received all the problems in a random order. And at the end of this experiment, he measured students' correctness on each step as they were solving the problems within the tutor, as well as their performance on a post-test that they took after they finished using the tutor. So this is the task that we would like to model, and we might like to be able to say things about which of these different kinds of interventions, either the blocked or the interleaved, is going to be better for student learning. So to simulate learning for this fraction arithmetic tutoring system, we used a computational model of learning that we built using the Apprentice learner architecture. And I won't say too much about this architecture in detail, but I just want to give you sort of a high-level conceptual sketch of how the model that we're using works. So first, the model interfaces with the tutoring system using the interactions that I've highlighted here. So first, it perceives a state of the problem. So this might be the state of a fraction arithmetic problem. And in response to seeing the problem, it either attempts a step, or if it doesn't know what to do, then it will request a hint or an example. In the case of a tutoring system, it's common practice that if a student continues to request hints, that eventually you just show them what to do next. So you get like a worked example. And in response to this, either the attempt or the example request, the tutoring system will provide feedback to the system on whether its actions were correct or incorrect. And if it requested an example, then it will give it an example of what to do next. So to learn from these interactions, the model uses a number of different memories, performance, and learning components. So the model closely aligns with the standard model that people have been talking about throughout the conference. So it has a short-term working memory. It also has a long-term skill memory, and it has a skill matching and execution component shown at the top there. And in this sense, we can think of it as a pretty standard production rule-like system where skills are represented as if-then rules. You know, they match against elements within the working memory, and they fire to either produce effects in working memory or to take action within the world. In the current system, it also has some additional learning and performance components. So first, I just want to talk about this example explanation component on the bottom. So in the cases where we get a feedback or an example of what to do next, the system first constructs an explanation of that example. So it does that by chaining together the skills that it has in its long-term memory in order to try to come up with an explanation that would essentially come up with a plan that would produce the example that it received. And then the sequence of skills that it found that explains that example get compiled using an explanation-based learning approach to produce a new skill. And across both skill matching and example explanation, the system is using a reinforcement learning system, which really what that reinforcement learning system is it's determining which skills should fire next. So it's learning the rewards for the skills that govern how conflict resolution is done. And then as the agent is taking actions both internally and externally, it's updating its estimates of the rewards for those skills so that it can do better in the future. So just to give you an example of what this looks like, here's an example of one agent in the interleaved condition. So first, the agent receives a fraction addition problem with same denominators. And initially, the agent doesn't really have any knowledge, so it starts off by just asking for a hint. And in this case, when it asks for a hint, the tutor tells it to put a 7 in the box. And from this, it constructs an explanation of that 7, and then it compiles that into a new skill. And this process repeats for the numerator and then also for the done button. So then we give it another problem with another fraction addition problem with the same denominators. In this case, it's using the skills that it just learned. So it tries applying those skills and taking some actions within the environment, and it's getting correctness feedback. So it gets the steps correct, and the tutor marks them green to let it know that it got those correct. So then we're going to mix things up a little bit, and we give it a fraction multiplication problem. And in this case, the system is going to incorrectly try the skills that it learned before. So it tries copying the 7, it tries adding the numerators. And when that doesn't work, it requests hints. And from those hints, it explains those examples and it learns new skills. And then we're going to mix it up again. So now we'll give it a fraction addition with different denominators. And in this case, it's going to, again, incorrectly overgeneralize. So it's going to try applying its multiplication and addition with same denominator skills. And when that doesn't work, it'll start requesting hints. And then it eventually learns how to do the conversions. And if we speed this process up, we see that it eventually converges to getting all the steps correct, even as it's switching between different types of problems. So in some previous work, we ran the simulations for all of the students in the 2 different conditions, the blocked and the interleaved condition. And this is a model that was slightly different than the one that I'm presenting today, but I still want to talk about this real quick. So the system it actually showed that the model was able to predict the main experimental results that Ronnie had. So in particular, it showed the model predicted that the performance within the tutoring system, on the graph on the left, would be better within the blocked condition than in the interleaved condition. So the idea is that when you're working on the same types of problems all together, you get really good at repeating the same steps again and again. So doing all the fraction addition with same, and then when you switch to fraction addition with different, you quickly get really good at doing those. But that blocked instruction actually resulted in worse performance on the post-test. And the performance on the post-test was actually better in the interleaved condition, because the system is learning. It actually gets more experience. It gets more negative examples from switching between the different problem types and producing incorrect generalizations that it gets feedback on. So it actually learns better concepts from the interleaved instruction. So our model was able to make these predictions, and when we compared it with the human results, we found that humans also have this effect where they do better in the tutor and the blocked condition, but they have better post-test performance in the interleaved condition. So this was some pretty exciting results. But there were some issues with this previous model. So when we started diving down into the learning curves, so this is showing the average performance across all of the simulated agents and human agents in the interleaved condition on the left and the blocked condition on the right. And one of the big differences between the simulated agents and the human agents was performance when they see skills that they have never seen before. So all of the simulated agents start off with essentially a blank slate. They don't have any prior skills, just some prior knowledge, in this case of whole number arithmetic, and from that they learn fraction arithmetic knowledge. Whereas the humans coming in clearly have some prior knowledge. I mean, they're achieving less than 50% of error rate on the first problems. So what part of the motivation for this work is to try and come up with a way to account for these differences in the prior knowledge between our agents and the humans. So our approach looks at individualizing the models to each of the specific people using their available performance data. So to do this, we framed this idea of figuring out what's the prior knowledge that each person has as a hyperparameter optimization problem. And then we used an existing toolkit out there for doing hyperparameter search called HyperOpt. It's just a Bayesian toolkit for intelligently searching this space in an iterative way. So the way that this works, if you look at the figure on the bottom, is we provide a space of prior knowledge and model parameters that we want to search. The HyperOpt toolkit will sample from that space and give us some prior knowledge and specific set of prior knowledge and model parameters that we load into our model. And then we run a simulation with our model to generate one of those learning curves, and we compare those to the human performance. And then we look at the differences between those as the loss between the model and the human, and we feed that information back into HyperOpt, and HyperOpt will then intelligently sample a new set of parameters that's slightly more informed. And we repeat this process multiple times in order to come up with an estimate of what the prior knowledge and the model parameters are that fit a specific person. So we wanted to evaluate this approach to see how well it works at tuning our models to fit specific people. So we provided it with a space of possible prior knowledge that included both whole number as well as fraction arithmetic knowledge. So, since some of the students are coming in already with fraction arithmetic knowledge, we put that into the space of possible prior knowledge. And then all models have knowledge for interacting with things like interface buttons and some other simple relations like determining whether or not two values in the interface are equal. And then we conducted 2 evaluations of our individualization approach. First, we evaluated the model on 24 students by fitting the model in the first 10 problems and evaluating it on the same 10 problems. So this is like, we didn't cross-validate, but the idea here is to understand if the model is actually fitting to the data that we're giving it. And then after that, we conducted a second evaluation where we did a form of temporal cross-validation. So we fit the model on the first 5 problems, data from the first 5 problems that we had for each student, but then we ran a simulation where we ran the learning for 15 problems and we only looked at comparing the human and the model on the later 10 problems. So this is testing it on a different set of problems than we used for the model evaluation. And our initial results show that when we trained and tested on the same data, the individualized models have a lot less error than the baseline model, which is just no knowledge, only whole number arithmetic knowledge to start. And then those results seem to transfer pretty well even to the problems that were different from the model, the problems that we used when we were tuning the models. So this is a good result, basically showing that model individualization does improve the predictions of our models for specific people. So next, given that we have this individualization approach, we wanted to explore how well these individualized models could be used to make predictions for how different students would respond to different possible interventions that they might receive. And we really wanted to look at this, the performance of these models at the individual level. So we just focused on 2 specific students. We looked at a high-performing student that came from the blocked condition and a low-performing student from the interleaved condition. And what we did was we individualized our models to fit each of these students. And then we conducted simulations to evaluate how well these 2 models our models predict how well these 2 students would perform for these 3 different conditions. So we evaluated them on the blocked and the interleaved, which I mentioned before, but we also wanted to evaluate them on a faded instructional condition for which we don't have any human data, but just really to show this idea that we can test a novel intervention that we might not have any data for. So the faded condition combines blocked and interleaved together, and it starts off with small blocks that gradually fade to interleaved over the course of instruction. So here, I'm just going to show the learning curve results for the human shown at the top here. This is the low-performing student. So the top graph shows the learning curve for the human, and the red line is their average performance across all of this is averaging over multiple skills, but it's showing like their performance on the first time applying all skills, the second time applying all skills, the third time. So the red line is the average, and the blue is a regression model that was fit to the data. And then on the bottom, we have the predictions from the model for the 3 different conditions. And you'll see that there are error bars there. What we did was we ran 20 simulations for each condition, and there are differences. Sometimes the model explains things differently, or it makes different mistakes, and based on the feedback and the poor explanations or good explanations that it has, it'll have different performance. So there's some variation. And so what we find here, first, if we compare the factual learning curve at the top to the interleaved in the middle there, so the low-performing human was in the interleaved condition. So if we compare those 2 together, that's like the most direct comparison. We can see that the model does a pretty good job of predicting the performance. And in particular, we don't see the large discrepancy between error rates on the first opportunity that we were seeing before. Next, if we look at the simulations across the different conditions, we find that the error rate in the interleaved condition is slightly higher than the error rate in the blocked condition, which agrees with the finding that we had before from the human data. And finally, we found that the faded condition seems to have the lowest error rate overall as compared to the blocked or the interleaved. So that's an interesting prediction of our model that we might test in the future with the follow-on human experiment. So next, if we look at the performance of the high-performing student, the performance looks a lot different here because the high-performing student already seems to know most of the fraction arithmetic knowledge. So one high-level finding from this is that it almost doesn't matter what kind of instruction you use for the high-performing student because they already seem to know most of the knowledge. Now that being said, the predictions from the model, when we compare across the different conditions, there are some differences. Mainly the interleaved seems to exhibit this like a spiking. You can see the little spikes in the error rate at the tail of the interleaved condition. Now this is as the model is switching between different problems, there's some kind of overgeneralization going on where the system actually makes additional mistakes. So we might predict that the human students might have slightly higher error in the tail of their performance as well in the interleaved condition.
3 minutes.
Oh, is that the 3-minute warning? Thank you. So finally, it's hard to tell from this figure as well, but we did find that the faded condition also has slightly lower error rate than either the blocked or the interleaved condition across our simulations. So again, this idea that our model is making a prediction that this faded blocked to interleaved instruction is going to produce a lower error rate within the tutor that we might test with our future human experimentation. So just to conclude, we demonstrated the use of these apprentice learner models for testing different fraction arithmetic training interventions. We developed an approach for individualizing these models to specific students using existing data that we have about those students. And so we constructed an individualized model for a high-performing and a low-performing student. And then using those models, we generated predictions about actual conditions that they were in, as well as untested counterfactual interventions that they could have received. And our model makes some plausible predictions about these counterfactuals that we hope to be able to test with future human experiments. And as far as our future work, I think one of the things that we'd like to do next is to pre-register some of the predictions that are coming out of our model and actually run this novel faded condition so that we can compare it to blocking and interleaving to see if the human performance agrees with the predictions that are coming out of our model. Additionally, we want to explore the use of the model for designing optimal instructional sequences. So here we're using it to evaluate different sequences, but taking that just one step further, we might have some way of iteratively working with our simulated agents the idea would be that we would learn a model for a specific person, and then we could like iteratively modify the instructional sequence that we feed to that model. We can keep running simulations in order to come up with an instructional sequence that's optimized for the model that we have for a specific person. So the idea would be to come up with like, what's the optimal sequence for person A? Next, we're looking at testing our model's ability to make predictions about a few other learning effects. So we're looking at things like the testing effect, where student performance improves after taking tests, even if they don't get any feedback or instruction during test taking. So we've been trying to make changes to our underlying model to account for these different kinds of effects. Additionally, we want to expand our approach to support other kinds of learning environments, such as educational games, in addition to tutoring systems. And finally, we're looking at exploring ways to make these kinds of models more accessible to real users, such as teachers or instructors, so that they can employ them to improve their instruction. So with that, I will take any questions. Thank you.
Thank you, Chris. There are a few questions. The first one is from Justin Lee. The evaluation of your models seem to mostly be about whether it gets a question correct or incorrect. Have you considered looking at the kind of errors that are made for incorrect answers?
Yeah, so this is a great question. Thank you. So we have been looking at this. There is actually a paper that is by, if I can send it to you in the chat afterwards or in the session afterwards, by Danny Whitcomb, that he actually does look at the different kinds of errors that our model is making and compares the types of errors. So like omission errors versus commission errors, whether the agent is making errors by hinting, like it's making errors because it's asking for hints more often than humans. And so he does an analysis that actually compares the different kinds of errors. And there are meaningful differences between our model and the humans. So I think there's definitely work to be done there.
Okay, here is another question from Michael Cox. Have you thought about how this kind of work can be generalized to A/B studies of groups of people, for example, teams?
Yes, thank you, Michael. We're actually looking at that right now. We are approaching it from the perspective of a multi-agent simulation. So there's actually another data set that I've been eyeing for a while that's very similar to this fraction arithmetic data set that is collaborative tutoring. So it's collaborative learning, not just collaborative performance. They have two students that are located at separate computers, and they're each interfacing with a tutoring interface, but it's kind of like Google Docs, so each student can see what the other student is doing, but the tutoring system is actually explicitly manipulating social aspects of the interaction. So like some students can only modify certain fields. The other student can only modify other fields. So they force people to take different roles during the problem solving process. So one idea we had is that we would be running one of these simulations for each of the students. And they would be interacting through a shared task environment that each of them might have different ability to manipulate. So we've been looking at some of that, but generally our idea would be to look at some of these social effects through like a multi-agent simulation, where we're actually simulating each of the individuals.
Okay, the next question is from Pat Langley. Do you really mean optimal sequences? Do you believe that is possible?
Great question, Pat. It's a challenging thing. I think in terms of picking out the sequences, I think the aspiration, let me put it that way, would be to get closer to a sequence that would be optimal for a specific person. So if you know what they know, and you know some other aspects of maybe some other parameters of their cognitive system, like how much effort they exert into explaining an example on average, and based on those things, I think you could construct better sequences than others.
As you know, I'm all for improving things. I just don't like the O word.
Yeah. I mean, I think of it, the optimal as an aspiration. I'm not sure if it's actually possible.
There are plenty of people in the AI community who think otherwise. That's why I'm concerned about its use. Yeah.
Well, there is some interesting work right now by somebody named Cheyenne Durruti on using some of they would think of it as an optimal sequencing problem, using some of these optimization techniques to come up with the best way to sequence problems. But their models that they're using are very high level abstract statistical models. So they're often very similar to the models that they're using to.
No. There's no.
Go ahead.
Pat, I think we lost you. Okay, I think we're also running out of time here. So Chris, you might want to connect back with Pat offline. Matt, I'll hand it back over to you.